In this video 263, I'll be talking about electromagnetic waves. This will be our introduction to this chapter, which is on light. Electromagnetic waves, also called EM waves for short, consist of rapidly oscillating electric and magnetic fields. As you can see in this picture, you have an electric field here and a magnetic field here, and they keep oscillating. What produces these waves are accelerated charges. We learned previously that a charge produces an electric field. We also learned that when it's moving, it produces a magnetic field. So it makes sense that if you have a charge that's being accelerated, that the field that it's going to produce is going to keep oscillating as the wave propagates. All electromagnetic waves travel at the speed of light. This is indicated right here. This wave that has the fields oscillating perpendicular to the direction of motion, but the wave itself is traveling at the speed of light. So in a vacuum, the speed of light is 3 times 10 to the 8 meters per second, and this number is directly related to the permeability of free space and the permittivity of free space, two constants that we saw related to the magnetic field and the electric field. The other thing I wanted to mention about the speed of light is that in general, the speed of any wave is related to the wavelength lambda of that wave and the frequency of that wave. So since we're going to be talking about electromagnetic waves that travel at the speed of light, we're going to replace the speed v by the constant c. This expression is going to be useful in the following slide. Here we have the electromagnetic spectrum. So this diagram here, this picture, organizes all the different types of electromagnetic waves by their frequency. So if we look at the expression that we just saw, that the speed equals the wavelength times the frequency, since the speed is a constant, we can solve for one of the other two variables, such as wavelength, and we get the speed of light divided by the frequency. So what we see here is that all the waves are ordered by frequency, but as the frequency increases, that means that the wavelength decreases. So by being ordered by frequency, these waves are also all ordered by wavelength. Increasing frequency on the bottom means a decreasing wavelength on the top. I like to look at these pictures here that tells us a little bit about these different types of electromagnetic waves. So we start with the low frequency radio waves. These are the waves transmitted by your radio stations. Low frequency means a high wavelength. The wavelength of these waves is about the length of a soccer field. If you remember the definition of wavelength, if you have a wave here, that is the distance from one part of the wave to the other identical part, from crest to crest here. That's the wavelength. So very large wavelength and a small frequency. And then we move on to higher frequencies. Microwaves, this is used to cook your foods. Also radar also use microwaves, right, to catch those speeding cars on the highway. So it's just an electromagnetic wave that has a higher frequency than the radio waves. After that, we have our infrared waves. These are produced by anything that emits heat, such as people. If you have special types of night vision glasses, you're actually able to see these. But the only types of waves that our naked eye can see is the visible light. So this is a very small range of frequencies, as you can see, compared to all of these frequencies here. Visible light is just a very small range of frequencies, which means it's also a very small range of wavelengths that we are able to see with our eyes. And then we move on to the higher frequency ultraviolet radiation. This comes from the sun. This causes sunburns. Then even higher frequency, we have our X-rays, used to see bones and teeth. And then finally the gamma rays with the highest frequency here. Radioactive material emit these, and one use is to kill cancer cells. but there are other uses as well. But this is just a very brief introduction to show you that accelerated charges can produce many different types of waves depending on the frequency of that wave. So just to summarize the electromagnetic spectrum, there's no sharp division between one kind of wave and the next. As you can see in the previous slide here, there is some overlap between the waves, but the spectrum does organize the waves according to their frequency, or you can say according to their wavelength. And finally, I wanted to highlight the fact that the visible light is just a very, very small part of the spectrum that we can actually see, and the range of these wavelengths is from 400 nanometers to 700 nanometers. We'll see these numbers again. Maybe we'll solve for the wavelength of a light when we do a problem, and then we'll see that we do get a number between this range for visible light. The last thing I wanted to go over is one quick U-turn here. It says light waves travel faster than radio waves. Is that true or false? So the purpose of this question is to realize that light wave is an electromagnetic waves, and so are radio waves. So if they're both electromagnetic waves, then they all travel at the speed of light. So they all have the same speed, so that means that this statement was false. So this was just a quick introduction to electromagnetic waves, and now we're going to be able to talk about light starting in the next video.